This right here is simply the lightest material in the world. We're going to learn about the famous aerogel. This substance that's 99% air. It's practically a solid cloud, a high-tech material that's even used by NASA. And the coolest thing is it can withstand up to 4,000 times its own weight. Really? Let's test it. I've wanted to get my dirty paws on this thing for a long time. This is the famous aerogel. Maybe you've heard of it, because it generated a lot of hype on the internet some time ago. We managed to buy a little imported jar with a bit of aerogel. Only one piece is a bit bigger. The rest are just tiny crumbs here. And this thing cost about 200 Rs. It was expensive, but as soon as you open the jar, you can tell it's something really special when you hold it in your hand. The first thing you notice is that it's extremely light. You can barely feel its weight. You only feel that there's something in your hand because it's hard. It's hard like a little stone. When you squeeze it like this, it's not soft. It's not something you squeeze like the foam inside a pillow, no. It's really solid. Another thing that makes it really beautiful is that it's kind of transparent. You can see through the aerogel. So it gives the impression that you're holding a piece of gel, like actual hair gel, in your hand. Look, it's solid. And I still think the sound it's making here is cool. It's kind of strange. It's the sound of things that are really hard. Let me put the microphone closer, but I'm afraid of breaking it. In the end, it kind of feels like a weightless ice cube. But actually, this is more like a hollow piece of gelatin. Look at this. Aerogel was invented in 1931 precisely because of a discussion about gelatin between two American scientists. Gelatin is a gel. It's liquid on the inside. It has liquid, but it also has a structure that is solid. It's a kind of very thin skeleton. That's why it wobbles like that when you shake it. What these two scientists were discussing was whether it would be possible to remove the liquid part from the gelatin and leave only the solid part, just the thin little skeleton that forms the gelatin. And one of them succeeded. The inventor of aerogel is a chemical engineer named Stephen Kissler. If he simply removed the liquid from the gelatin, it would collapse. So he had a very different idea. He sealed the gelatin inside a place where he could greatly increase the pressure and temperature. At the moment he removed all of that, the liquid inside the gelatin turned into gas. It disappeared and was replaced by air. And then we end up with a very, very, very minimal solid structure. And inside, it's practically 99% air. We have an aerogel. This little skeleton can be made from several different materials. You can make it with carbon, or you can make it with cellulose, which is the same material as cotton and paper. And you can make it with silica, which is basically the same material as glass. The one we have here is made of silica. It's not the lightest of all. The lightest of all is the carbon one, but it still has all the special properties of an aerogel. Let's start doing our tests. First thing, how much does this thing weigh? It does have some weight. It's strange to compare it with other things because this is completely irregular. So I got a little stone that I have back here, made of niobium. It's the same shape. Looking at it, they take up the same volume. This little niobium stone weighs 93.4 grams. So, how much will the aerogel stone weigh? 0.5 grams. 1 gram this here is half a gram. Moment of truth, huh? Shall we see? Exactly 1 gram. See, I told you, it's extremely light. But, Bert, give me a break, would you? You're comparing it to a piece of niobium, which is one of the densest things you have there. It's like lead. And instead of comparing it to something lighter, right? Does cotton count? Gram. Cotton is one of the lightest things we know. Pretty much the same shape here. The same volume as the aerogel. It weighs 2 grams, twice the weight of the aerogel. 1 gram, even though it's so light. Theoretically, this little piece of aerogel could withstand 4,000 times its own weight, which means we could put a 4-kilogram object on top of it, and it still wouldn't deform. I'm not going to do that test yet because you see it's a test that would probably damage our little stone here. Before that, I want to try two more things. The first is to observe the color of this. I'm going to get my phone. Where is it? Where is it? Is the phone around, Jansen? Thank you. You can also see Julia's foot and Jansen's foot back there in the background. You can notice that the aerogel is a very light blue. It actually looks a lot like the color of the sky, but it's not exactly like that. Because if I hold it up to the light, it turns kind of brown. When removed from the light, it turns blue again. So, after all, is it a brown or a blue substance? Blue or brown? Aerogel works exactly the same way as the sky. It's blue. Is like blue of our sky. And the brown is like a sunset. So it's pretty much like I'm holding a piece of the sky in my hand. So, let's remember why the sky is blue. The white light we see coming from the sun is actually made up of the colors of the rainbow. So I'm going to draw it right here. Violet, blue, green, yellow, orange, and red. Iber, your rainbow has 6 colors instead of 7. It's missing the indigo chalk, but indigo, let's agree, it's just a kind of blue. There's no such thing as indigo. There's no indigo chalk. Have you ever seen anything indigo? Yeah, I've never seen anything indigo either. You don't buy an indigo car. There's no t-shirt that says indigo. Have you ever seen indigo jello at the supermarket? What happens to these lights when they pass through the air? When they pass through the Earth's atmosphere, the ones closer to blue, especially blue and violet, they start to scatter. This light here, when it passes through the air molecules, it scatters in all directions. But the other colors keep traveling, so if you're here and look at the sky, what you'll see are those colors that have scattered. You'll see the sky blue, because blue and violet have been scattered by the atmosphere. On the other hand, when the sun is setting and the light has already passed through a lot of atmosphere, when you look at the horizon and the sun is setting, you're seeing the sun behind an enormous layer of atmosphere. You'll see it around here, right? And what you'll see are the colors that are left because the blue and violet are already gone. They've already been scattered. So, what you see is a sun that's much less white and much more yellow. And that's exactly what happens with aerogel. When I look at this from a distance, from the position I'm looking at now, the light that's coming from various directions here, it scatters. The blue light that's coming in scatters. So I can see the blue coming out of this object. But on the other hand, if I look against the light, this is what will happen. The blue light can't get through. So I see the light that's left, which is basically more red than blue. In this case, it ends up looking kind of brownish. Just for the record, this is called Rayleigh scattering. And by the way, you can also see it under the microscope, because this microscope here has lighting from below and above. We can see aerogel in 2 different ways. Let's see if I can do it here. Look how cute that is. Cute little aerogel. Look, here we're seeing the aerogel from above. It becomes almost transparent, like a piece of glass with a slight brownish tint. This light is coming from below. It's coming through the aerogel. Here's what's happening. As if I were looking through here, I'm going to see the brownest part. If I reverse the light, put the light on top, we'll see, look, blue sky. It turned completely blue. It looks like a little piece of ice. That's cool. That's really crazy. I really wanted to try to see those pores in the aerogel, right? See if we can see that skeleton, because so far I can't see it. Let's zoom in a lot here. It looks like a little piece of glass, right? Yeah, even at the microscope's highest magnification, we still can't see those pores. So, it's a structure, a network that exists there that's extremely thin. Because if we can't see it even with this huge magnification, it's because it's really very small. Another thing we really wanted to see is the aerogel under ultraviolet light. We won't be able to see exactly what ultraviolet does to it because we can't see ultraviolet, but the light that's very close to ultraviolet, which we can see, which would be this violet here, it doesn't pass through the aerogel. So it's opaque to this kind of light, theoretically. We have 2 lights here that represent the ends of the rainbow, okay? On one side, a violet light, and on the other side, a red light. When I put the violet light up here, you can see that we can't read the words behind the aerogel. So you can see down there, look, with the violet light, you can't see what's behind it, right? That means It's completely scattering the violet. The violet can't pass through the aerogel. Now, I'm going to use the red light. And look, we can read what's behind it. It becomes transparent. It scatters the red light less. You can see it clearly here. So, this one is the red light. It's able to pass through the aerogel. And this one is the violet. Another thing we noticed is that when we shine the red light, the aerogel practically doesn't cast a shadow. Julia, turn on the purple light. Look, there's a really strong shadow. You can clearly see the shadow. Now, with the red light, look, almost no shadow at all, LD. The light passes through the aerogel. We had paused the recording to take a picture of the aerogel. People here at Manual do Mundo say, I have a vise grip. It means I grab things with a lot of strength. So you probably guessed what happened, right? Before, we had a beautiful block of aerogel, and now we have the magic of multiplication. 2 blocks of aerogel. At this point, you must be wondering, okay, the thing is nice, it's interesting, but what is this gadget for? Aerogel is useful because it's very light, and it can also absorb extremely violent impacts without breaking the objects involved. For example, between 1999 and 2006, there was a NASA mission called Stardust, and the idea was that this mission would be able to collect little pieces of comet that were traveling through space. The problem is that this little dust, this stardust, travels at about 6 kilometers per second. That's about 22,000 kilometers per hour. So, who would be able to catch something like that? What they did was put a piece of aerogel outside the spacecraft. When these particles hit, the aerogel would gradually cushion them. It would work like a kind of very slow brake. It's as if the particles entered there in slow motion. They would hit, but they were hitting something that wasn't strong enough to destroy the particles they wanted to study. The aerogel served as a kind of super powerful padding to store these particles without breaking them. But that's not all. This structure, like a kind of gelatin skeleton that only has air inside, makes aerogel a terrible conductor of heat. Or, in other words, it's a great thermal insulator. It doesn't let heat pass through. So, it's also used by NASA in those little robots, those rovers that go to Mars. The temperature can range from 125 degrees Celsius to 20 degrees Celsius. So good thermal protection helps protect the electronic components. Nice theory, right? But can this little guy really handle it? Shall we do a thermal insulation test here to see if it holds up? It was supposed to be a bit better than this, but I already broke the aerogel in half. So we're going to do something that Derek from Veritasium did, which is try to melt a piece of chocolate on top of the aerogel. I'm going to take a piece of chocolate and put it on top of it. And the idea is that I can light a flame underneath it. The heat won't reach the chocolate. It's hard to believe this will work, but let's try. I need to hold it somehow. It's smaller now. We'll clamp it with this little claw. See? Let's see. Oh my god. Wow, it really holds up to the fire. I thought it would get ruined by the fire. Damn, what temperature is it? 150 degrees Celsius.
50 degrees Celsius for the aerogel, 31 degrees Celsius for the chocolate. Wow, guys.
Wow, it doesn't transfer the heat to the chocolate.
That's incredible. It's in direct contact with the fire. Chocolate 38 degrees, the aerogel at 170.
Eventually, the chocolate will melt.
Yeah, at some point it will.
But also because the flame goes around the aerogel. Right, look at this. Wow, it holds up. Huh. That's cool. Do you think I can touch it? Does it have low heat capacity? Will I burn my hand?
No, I don't think you'll burn yourself. But still, be careful with the chocolate.
What? Do you think aerogel is hot enough to burn my hand?
Yeah, I think so. Up here, it's not hot.
No, it doesn't have any thermal capacity at all.
Guys, it's not hot. It's just warm.
What's it reading there? 108 degrees Celsius. 108 degrees C, and we put our hand like this and don't feel anything. Yeah, the heat capacity is very low. It can't hold the heat to transfer it to our hand.
Mentioned the heat capacity of the material, but actually capacity is how much heat this material can store. But in the case of aerogel, it's not special because of its heat capacity or anything like that. That's not the point. Actually, it has low thermal conductivity. And what does that mean? The material does get hot, the aerogel gets hot. It heated up, you saw it on the camera. It heats up, but has trouble transferring that heat. So when touched, it doesn't warm your hand quickly. It takes much longer than typical materials. So the magic of aerogel is its low thermal conductivity, not its heat capacity. I'm in shock.
It's really crazy.
Can't believe this.
Whoa. You couldn't expect him to handle that. Oh, wow! Hold on. This part here that's already burned. I think it's already compromised for us to do the last test, which is the resistance test. I don't think it's as strong as I thought. Theoretically, how much can it handle? 4,000 times its own weight.
Yeah, from 2,000 to 4,000 times, but
From 2,000 to 4,000, so the statistics have already dropped. Yeah, they've already dropped. Let's make a triangle, then, with 3 points, and we'll put the weight on top. Let's weigh it. Let's weigh it first. These 3 pieces weigh 0.55. So, theoretically, they were supposed to hold 1 kilogram just for starters to begin with. At least one. Let's start with the Manual do Mundo book here. Come on. I'll get our smallest book, which is Guia de Sobrevivencia Natureza. How much does the book weigh? 253. 253. Yeah, this little book should hold. Come on. It'll hold. Amazingly, this is nearly 500 times its own weight.
exactly. It seems like it's not much, but if you think about the fact that it weighs 0.5 grams.
It held up.
Wow. Every time we put it on, my heart can't take it, guys. I think I'm going to die.
How about a heavier book now? Guia do Astronauta para Dexaro Planeta, 412. And you have to add it up. 665. It made a little cracking sound there, but it held up.
Yeah, it's not on the floor.
It's not on the floor. No, hold on. This here, oh. Yeah, I think it definitely didn't hold up. Look at the state of the aerogel here on the table. My God, it's all shattered. There's absolutely nothing left. But today, we got to learn about the properties of this aerogel. Its color is really cool. Its resistance to heat is really impressive. But mechanical strength is not its strong suit.
Yeah, it's seen better days, let's put it that way.
Shall we put it in water to see what happens? I'm dying to put this in water. What do you think will happen?
I think it's going to absorb the water like this.
Is it going to absorb it? Yeah. I think before it absorbs the water, it's going to float, right? That's something. Wow. It turned white. Oh, it didn't float, Julia.
It's releasing a gas here.
I mean, it did float a bit, but it's releasing the air it has inside.
Wow, I hadn't even thought about that.
Wow. It turned completely white. Now, the light can't pass through the way it used to, right? It's passing through water as well. He turns white right away. I can't do it. I couldn't record it. It looks like it's boiling. The water gets inside him really fast. And look, it shatters completely.
Wow, it's instant.
It's instant. It sticks to the water. It's not hydrophobic. It's the opposite. Hydrophilic. It's hydrophilic. It wants water, so it pushes the air out and gets completely filled with water. And in the end, it turns into something really ugly. It becomes that goo that's actually pretty brittle, too. Wow. It turns white instantly.
Yeah, it turns into a kind of weird little paste.
It turns into a weird gel. I don't know, it looks like that diaper gel. So, its kryptonite is water.
Yeah, Manual do Mundo books.
Apparently.
Yeah, an Ibert.
Iber.
2.
I'm going to throw in everything else we have.
Sure.
All right. Do you want to see another really crazy material? About 13 years ago, we bought ferrofluid, which is basically a liquid that can react to a magnet, and then it takes on all sorts of crazy shape. It was in this video that I ruined my favorite shirt.